Welcome to the Explainer. When we talk about building an AI, our minds immediately jump to all the complex code, right? But before you write a single line of code, there's a much bigger, more fundamental question you gotta ask. What world is this AI actually going to live in?
I mean, think about it. An AI that's built to play chess is living in a completely different universe than one that has to drive a car on a busy highway. The goal is different, for sure, but the world itself is the real game changer. So, the very first thing you have to do is map out that territory. You've got to understand the world the AI needs to survive in.
And in the world of AI, this has a name. We call it the task environment. Basically, it's the AI's entire universe from its own point of view. It could be the chessboard, the highway, or even the stock market. And figuring this out, it's the absolute non-negotiable starting point for any AI project. Okay, so how do we actually do that? Well, we use this kind of blueprint, a set of 6 key properties that lets us classify any task environment. Once you understand these 6 dimensions, you know exactly what kind of challenge you're up against.
All right, let's dive right in. First up, we have Dimension 1, observability. This one is all about a simple question. What can the agent actually see or perceive in its world at any given moment?
So on one side, you have a fully observable environment. Think of this as the AI having a kind of godlike view. It can see everything it needs to know all at once. But on the other side, you've got partially observable environments. This is where crucial info is hidden. The agent is forced to guess or maybe remember what it saw before to figure out what's going on. A perfect example of fully observable is a chess game. The AI sees the whole board, right? Every piece, every square. No secrets. But a self-driving car? No way. It can't see around a blind corner. It has no idea if the driver in the car up ahead is texting. That world is only partially observable. And man, that makes the problem so much harder to solve.
A lot of that missing information, that lack of observability, it often comes down to our next dimension, agents. The question here is our AI acting alone? Or is it sharing its world with others?
A single agent environment is pretty straightforward. The AI is the only one in there making moves. But a multi-agent environment? That's where things get really complicated fast. Now the AI has to deal with what other agents are doing. And those other agents could be competitors trying to win, or maybe even collaborators trying to help. Think about solving a puzzle, like a crossword. That's a classic single-agent task. It's just you and the puzzle. But let's bring back our self-driving car. It is living in a massively multi-agent world. It has to deal with other drivers, predict what pedestrians are going to do, follow traffic signals, all these different agents acting on their own.
And all those other agents, they introduce a ton of unpredictability, which, you guessed it, leads us right into our third dimension, certainty. Is the world predictable or is it random? When an AI does something, is the outcome guaranteed?
A deterministic world is like a perfect machine. If you do X, Y always happens. No exceptions, no randomness. But a stochastic world, that's a world with a bit of chaos, an element of chance. The AI can do the exact same thing twice and get a different result because of random, unpredictable factors.
Chess is a great example of deterministic. You move your knight from one square to another, the board changes in one and only one predictable way, every single time. Driving, on the other hand, is super stochastic. A tire can blow out, a sudden rainstorm can slash visibility, a deer can just leap out onto the road. The AI has to be ready for just about anything.
So it's not just about what happens in a single moment. We also have to think about how actions link together over time. This brings us to our fourth dimension, experience. Is each decision a one-off thing? Or is it part of a longer story where what you did before really matters?
So, in an episodic environment, the world is chopped up into these little independent tasks or episodes. What the agent does in one episode has absolutely no effect on the next one. It's a clean slate every time. But in a sequential world, history matters a lot. Every single action is a link in a chain. A decision you make right now could have huge consequences way down the line.
Let's take a factory robot that sorts parts. Each part it looks at is a brand new episode. Its decision on the last part, good, bad, whatever, it doesn't change anything about the part it's looking at now. But chess is deeply sequential.
Your very first move can shape your entire strategy for the whole game. A small move now can lead to checkmate or disaster 30 moves later.
And in a sequential world like that, time is everything. Which leads us to a really simple but critical question. Does the world hit pause while the AI is thinking, or is it in constant motion? This brings us to dimension 5, change. A static environment is, well, it's polite. It basically hits the pause button, while the agent figures out its next move. A dynamic environment, though, is relentless. It is constantly moving, constantly changing, whether the agent does something or not. This means the AI can't just sit there and think forever, it's got to keep up. Solving a crossword puzzle? Totally static. The grid, the clues, they'll wait patiently for you all day if you need it. But our self-driving car? Its world is incredibly dynamic. While it's thinking about whether to change lanes, the cars around it are moving, pedestrians are crossing, and traffic lights are changing. It has to act, and act fast, in real time.
Okay, we're at our last dimension. And for this one, we're looking at the very fabric of the world itself. Are the possible situations and actions finite? Like, can you count them? Or are they basically infinite? This is our sixth and final dimension, the state and action space.
A discrete environment has a limited, countable set of options. Think of it like a menu at a restaurant. You have specific items you can choose from, and that's it. A continuous environment, on the other hand, has an infinite range of possibilities. It's more like a color wheel, where you can pick any shade, any tiny variation imaginable. So, let's go back to chess one last time. It's discrete. There are exactly 64 squares and a finite number of legal moves you can make at any time. But the self-driving car? It operates in a continuous space. Its speed, how hard it's accelerating, the precise angle of the steering wheel, these aren't just a few set options. They can be any value along a smooth, infinite spectrum. Okay, so we've just walked through all 6 dimensions of our blueprint. We can now create a full profile of any task environment. Now for the big payoff. Why does this matter? How does this blueprint actually help us build the AI?
Well, it boils down to a really clear 3-step process. Step 1, you analyze the world using these 6 properties. Step 2, you figure out just how complex that world really is based on those properties. And step 3, you build an AI that's the right fit. So for example, a simple puzzle world, fully observable, single agent, static, that probably only needs a pretty simple agent. But something like real-world driving, oh man, that's partially observable, multi-agent, stochastic, dynamic, and continuous. That environment demands an incredibly sophisticated agent, one that can build a model of its world, plan way ahead, and never stop learning.
This whole framework, it gives us a really powerful lens for looking at the frontiers of AI. And it leaves us with a pretty cool question to think about. If you use these 6 properties to measure complexity, what's the most complex environment we could ask an AI to master next? Is it something like navigating our own complex social interactions, making brand new scientific discoveries, or maybe trying to manage the crazy, unpredictable dynamics of a global economy? Whatever it is, this blueprint is how we'll start to figure it out.